Well, everybody, good evening. Allow me to pray. Just Lord, help me tonight. I need lots of help, and be with us and help us to learn and teach. In Jesus' name, Amen. Now, the first thing I want to do tonight is start out by showing you guys how to check out a transceiver. So, in the meantime, this is chapter 4I. A, B, C, D, E, F, G, H, I. This is the ninth time we've gathered together for chapter 4. I'm hoping that we can go through the rest of the classes quicker. Once we get these fundamentals down, we should be able to understand and proceed quicker with all the rest of the stuff that we've got to do. And just, I mean, you know, we're learning electronics. Tonight we're going to learn about fields. We're going to learn about capacitive voltage fields, and we're going to learn about magnetic fields. And everything, well, now I might have to take that back. Everything in analog amateur radio has to do with fields, capacitors, charges, inductors with magnetic fields. When we have an oscillator, it creates an electric field moving back and forth. When we transmit, we create a field from an antenna that's a magnetic field, and it has a electrical field that's perpendicular to it, and we line our antennas up that way. I mean, it just, when we get to each one of those subjects, you will understand why we spend so much time on what we've been doing. So I want you to remember this. Remember, power is equal to E squared over R. So we're going to check a transceiver, and I'm going to go through that quickly one more time. And also this is a similar signal generator to mine. And we will test the sensitivity of a radio. Now, most of this equipment will remain here, the oscilloscope and some other things. I'm also going to show you tonight other types of equipment that you yourself can purchase to do these things. Now, some of you will never want to do this, but I know that some of you, especially the ones going for extra class, will want to be able to set up and do this for the various kinds of projects that you've got going. So let's go to a different microphone. I mean, not microphone, excuse me, a different camera. Okay, I want to show you this. Now, folks, I kind of turn around and look at what I'm showing here. This is a dummy load. This one will take 100 watts continuously, and it belongs to the club, and you can use that. Now, with this dummy load, we have a transceiver here. That we're going to test. And we've been using this for showing S levels and how dB works. So tonight we're going to test the power output of this. So coming back over here, if you have your own radio, and you want to test it, you can use this equipment to do so. Now here is the load. This is a T. Now this could be just a BNC T, but I happen to have this general radio connectors, so I use these, but it could be a BNC. This is a BNC adapter, and this is a PL259 adapter on this end. And this here is just a plug that an oscilloscope probe will fit into. This is for the older style here, and this is for the newer style. So when we talk on the transmitter, this dummy load will take the load and won't transmit over the air. And then we have the probe for the oscilloscope to show. So, all right, now this is the oscilloscope. I have the vertical set up for 50 volts per division at 2 milliseconds, which is great for audio. So when I talk into this, and I'm going to turn this up so you can see it. Turn around and look. A little too bright. How's this? Yeah, okay. Now we can see this is 50 volts per division with 0. When I'm not talking, it's at 0 volts. And then when I talk, it reads like that. So this is 50 volts, and that's 100 volts. But since it's that low, I'm going to change it to 20 volts per division. Now notice 0, plus, and minus down here. So the peaks are hitting about right here. So if we look at the scale, 20, 40, 60, hello, it's about 70 volts. So if we use a calculator, and who out there wants to tell me what the formula is? Nobody? Not one taker? Daron?
I want to tell you, but I don't know what it is.
Oh, for power? Peak envelope power?
No, sir.
Oh,
Sorry.
well. Okay, well. I'm going to turn this guy on.
E squared over R?
Yes. Thank you, Scott. My calculator. So, well, we're going to take 70, but what do we do with the 70 first?
0.707.
Yeah, we do. What do we do with that? We multiply by 0.707, which gives that. What does that give us? Anybody know? Does anybody remember RMS value?
Yeah, right.
Now you remember. So that's 49.49. Now I changed my my calculator this way. So I take 49.49, which is the RMS value of the peak. So we go from 0 to the high point, which is peak. We multiply that by 0.707, and then we square that. So I'm going to hit x squared here. And then I'm going to divide that by the resistance, which is 50 ohms. And that equals 49 watts. Pretty doggone close to 50 watts, which is what this transceiver is designed to do. Does anybody out there think they could actually test a rig?
Yep.
Sure.
Good. And Darren, you can't use your monitor.
I just don't get this precise. I don't really care whether it's 49 or 50 watts, so long as it's got some power coming out of it.
Well, right, we want to know if it's supposed to be 50 watts and it's only putting out 35, then or 25 or something like that, then we know there's something wrong.
Absolutely.
So, you know, if we can come close, that's what we want to do. And in fact, I'm going to talk about that in just a little bit, about various ways that we can figure out how this works. So now we're going to check the sensitivity of this. And I need to change my camera again. This is my signal generator. Is it still in view?
Yes.
Okay, good. I'm just holding on to it here. Here is the attenuator for changing the output level. This switch turns it on. And this meter over here tells the level that it's set at, and you adjust it with this here. So for right now, I'm going to go back over here where the radio is. Now, what do I need to do with the radio? Anybody want to venture a guess?
Transmit.
Right. So I hook up the signal generator and I transmit it to it, right?
No.
Oh,
Into the dummy
Aaron,
load.
I'm just going by what you said.
Into the dummy load.
Yeah, but no, we're going to test the sensitivity of the radio.
Oh. We already did the other one. That's right.
Right. Okay.
So unplug the microphone so we don't transmit.
Right. Yeah, we get rid of the microphone. That way we guarantee we're not going to accidentally transmit into it. And then on the back side is the antenna connection. And I can disconnect the antenna. Because you want to make sure that you do not transmit into your signal generator. If this were a new signal generator, that'd be about $1,000 mistake. So now I'm hooking up the generator. And Darren, remind me when we get done here
Yeah.
to turn the musician thing off.
Okay.
But now, can you all hear that?
Yep.
Okay. Extremely annoying. But I'm going to reduce the input. Oh, by the way, there it is. It says S9. I think you might be able to see it. And that's 50 microvolts. So I'm going to take out 10 dB, 20 dB, 30 dB, 40 dB. Now it's down to 0.5 microvolts. Can you still hear it?
Yes.
Yeah. So I don't know if you guys can hear it, but I can still hear it. I can barely hear it at 0.05 microvolts.
Now I can hear it.
What was that, Scott?
I say I couldn't hear it down at .05, but you got a better advantage.
Yeah, this microphone I've got here, by the way, I'm going to give you one of these for your church. Is very sensitive, but it's not that sensitive. I can just barely hear it. But
Oh,
I actually have the equipment for checking the signal to noise ratio. I mean, the standard is 10 dB signal to noise ratio is the lowest voltage you can do. But you know, if you get down there and you got a signal you can hear well at a half a microvolt, that's plenty acceptable for about any transceiver, and most of them are significantly more sensitive. So anyway, if anybody wants to test their radio, they can come over here. I will meet you, and if you feel uncomfortable, I'll do the actual testing. But if you're feeling brave, I'll let you do it and run you through the process. I would like to get a handful of people who are able and willing to test people's radios out for them. So anyway, but let's get out of this and let's get back to my keynote. Now, the next somebody asked last week, well, what do you do if you don't have an oscilloscope? And this is what you can do. You can buy an SWR bridge. This one's by MFJ. It's $160 and it reads peak. If you had it on average when you're talking, what might peak at 100 watts would only peak at about 25 or 30 watts. So if you don't have a peak reading meter, you can't tell what your peak envelope power is. But this one will work up to 2 kilowatts. And they have another one that's about $130, and that's the least expensive peak reading watt meter that I could find. Now, this one, this is the newer brother of the one that I've got at home. And this one is the only one who has been tested by ARRL, and they tested a whole slug of them that accurately tells you what your peak reading is. But you know, as Daron and I were talking earlier, you know, if you're within 10 or 20% even, well, I'd say 10%. You know, that's plenty close enough for what we're trying to do. You want to find out if your 100-watt transmitter is putting out about 100 watts. I mean, if it's only putting out 35, you know you got some kind of problem. But notice the price on this, $350. Now that's a lot to invest. I mean, and $130 is a lot to invest for an SWR bridge, and a lot of hams do. But look at this. Scott, thank you. Scott told me about this, and I went online and I checked it out. In fact, I called the manufacturer to ask him about this oscilloscope. And I told him what we would be using it for amateur use and that kind of stuff. This is a 100 megahertz 2-channel digital storage oscilloscope. Now this is a storage oscilloscope. A lot of people don't know, but in the past, when I was working in the industry, that would have been a $3,500, $4,000 oscilloscope. This oscilloscope is $270. And they have another one, which is a 200 megahertz, which is $350. Now, if you got this and you had a dummy load, which you all should have a dummy load anyway, you could check your power output, and you can check everything else that you want to do that you could use an oscilloscope for. I mean, how many of you heard of a spectrum analyzer?
Yes.
Yeah, this thing has a spectrum analyzer built into it. It can, with this microprocessor, look at the analog signal. It converts it into a digital form, stores up to 64 megabyte of the signal, and then if you want to look at the spectrum, it analyzes using what they call fast Fourier transforms and turns it into a spectrum analyzer. So you can look at the output of your transmitter and see that it is operating properly. For anybody that's technically inclined, I would recommend you go with something like this rather than a $350 single meter. I will put a link to this company and these oscilloscopes with the video when I put it out. So anyway, anybody got any questions on testing equipment? Okay, decibels. One more quick note about decibels. We've studied them. Of course, they have all kinds of applications, as we should remember. But here's what you need to remember about dB. When you're talking about decibel, the power ratio, for every 3 dB, that's either 2 times or 1/2 the power. For 10 dB, that's either 10 times the power or 1/10 the power. So you can figure out in your head very easily how many dB gain or loss you have and how much you're gaining in power. If you had an antenna with a 10 dB gain and you transmitted 100 watts into it, that would be like having a 1,000-watt transmitter. That's much more efficient than having a dipole running 1,000 watts, and also a lot less expensive. Now, if you're talking about either voltage or audio, and remember our S units on our radios are in voltage, and S9 is considered to be 50 microvolts, and I would say that is true for most HF rigs. I don't know what happens in the VHF, but I've never actually checked for that. But for each S unit, that's 6 dB. And that's also 2 times the voltage or 1/2 the voltage. 20 dB is 10 times the voltage or 1/10 the voltage when you're dealing with dB. So, and this last one I've got here, you can see 50 microvolts is S9, S8 is 25 microvolts, and I've confirmed that. So, moving on. Now, a quick review of capacitors. Capacitors are storage devices. You can use them in power supplies for removing hum. You can use them in filters where you got coils and filters and resistors, so that you can have low pass filters and band pass filters, so on and so forth. You can use it as a DC blocker. If you're trying to couple one stage of an amplifier to another, and the DC is not correct to bias the next stage, you can put an AC, a capacitor in there. It'll pass the AC signal, but it'll block the DC. You can use it as a timer. And you remember Daron doing the time constant, where he applied voltage and we watched the voltage gain. And then we would drain the capacitor. So And also they're used in tuned circuits for oscillators, RF amplifiers, transmatches, and so on and so forth. Now here's when you charge up a capacitor and then you discharge it through a resistor. And here is a capacitive time constant curve. Now the one thing that you need to remember, you extra seeking people, 63.2% is one time constant on the charge side. On the discharge side, 36.8 is the percentage, but this one, 63.2% is one that you want to remember.
And if you had your Intech, you could probably see that happen right on the Intech.
Oh yeah, oh man. I should not get one of those because I don't have that much time to play. After this class is over with, I might have some more time. Okay, what's coming up tonight? We're going to talk about reactance. The capacitive reactance, X sub C, and inductive reactance, X sub L. We're going to talk about phase angle, and I don't think that we're going to get to impedance and resonance, but we will see. So capacitors, and right now I'm going to talk about fields. Capacitors store electric fields. When you store up a capacitor, it puts a charge on the capacitor. If you disconnect the power, the voltage will stay on the capacitor. It'll leak off a little bit slowly if there's a little bit of leakage in the capacitor, but generally it'll hold it. And I won't tell you what the kids used to do when I was young. And inductors store magnetic fields. So if there's a current passing through a magnetic field, and I will be showing you inductors here shortly with a compass, how that happens when you've got a field, magnetic current going through a wire and then a coil. So now why we need to know this? That what you're looking at right now is a radio signal that's being transmitted through the air. You can see there is a magnetic field, the blue here. When your antenna receives an RF signal that's moving back and forth, the voltage is in the antenna back and forth from the oscillation frequency. And it will send out this signal. It'll propagate away from the antenna. And then there's the electric field, which is perpendicular. And you can see this going like this. So if you've got a vertically oriented antenna on the receiving end, you want to have a vertically oriented antenna. And just quickly, if you're working in VHF and UHF and you're doing line of sight, if you got a vertical antenna, you should have a vertical antenna. If you got a horizontal antenna, you should have a horizontal antenna. So that you match. If you're going through the ionosphere, and boy, I tell you, once it goes up there, it gets twisted around in all kinds of ways, so it doesn't much matter. Now, inductance. I'm going to discuss that, and we're going to do a little bit of review in the process. Now, how many of you remember me talking about this? No one?
Well, a little bit.
Okay, Daron, hang in there. This shows what happens if you have a wire with a current going through it. This one shows the current going from positive to negative. And you see the arrow indicating. Now, what kind of current is that? Can somebody tell me?
I think you said that's whole flow.
That's right. That's whole flow. That's conventional current. So this means that the holes are flowing this direction, which means what? What are the electronics doing? Electrons doing?
It's coming back at you.
They're going the other way. They're going this direction. So they start down here and the electrons flow that way. Electrons flow from negative to positive. So we just have to keep this in mind. Now, this is a question on the extra test. It's E5D06 if you want to know. But they don't, in that question, they talk about electron flow. This, as we're looking at it here, is whole flow. So you use the right-hand rule. Imagine wrapping your fingers around that wire with your thumb pointed toward the negative side. So the direction of the flux lines is with your fingers. So if you are going to do electron flow from negative to positive, you use the left-hand rule, and then you aim it up your thumb up the wire toward the positive, and then your fingers are showing the direction of the flux lines. So remember that, and those associated questions for the test. Okay, now let's talk about inductance. When you run a wire, a current through a wire, it produces a magnetic field around it. If you take that wire and you wrap it like this has been wrapped around something, either air or a core of some kind, if you put a core on it, you will increase its inductance and its ability to be, for instance, a magnet. But let's illustrate what actually happens. So, okay. Now I want you to see what this is, because looking down on it, it's not. Oops, it's not apparent. But this is a hunk of wire, which I just lost my connection. Ah, got it. Now, what I'm going to do, I have a digital ammeter here. And I'm going to, I've got to come over here and adjust the variac. So I'm going to plug in the transformer. This being the transformer. Don't do this at home, kids. It's not UL approved. So I'm going to apply voltage to the transformer. And I don't know if you can see it or not, but I'm going to put 2 amps DC through this wire. There, I'm at 2 amps. Now, if I take a compass, if we hold it out over here, you can see it pointing north. But if I get it over close to the wire, see it bend a little bit? See that? So there's a magnetic field going around this wire, and it deflects the compass just a little bit. Now, let's take the wire and hook up a coil. Now here's an inductor. Believe it or not, that wire by itself is an inductor. But this is a much stronger inductor. So we've got the coil. Now, if we take the compass, oops, don't want to get too close here. Okay, now, and see, I bring it over here. Now, notice how much more it deflects the needle, because each time you wind a core, it adds to its ability. But I'll tell you, so, oops, here, wait a minute. The magnetic field of the earth is pretty strong. So we just move this over here and see how much it swings. So we've created a stronger magnetic field by having by coiling the wire up. Now the one thing about a magnetic field, and I'm just going to tell you this, I may illustrate it next week. If you had a wire, in fact, I'm going to show you now. If you had a wire right next to this, and it was a DC field, it would, when it first turned on, it would induce a wire, because the magnetic field would cut across this wire, trying to get this. The magnetic field would cut across the wire. In doing that, it would induce a current into the wire, which would create a voltage. Now, if you have DC like we've got right now, and we move the wire in and out of the field, it will induce a voltage into the wire. If it's just sitting still, it will not induce, it stops inducing a current into the wire. So your antennas, which are made up of a magnetic field and an electric field, are moving through the air, and they pass your antenna, and they induce a current into the antenna, which creates a voltage which your radio is able to receive. That's a very important concept.
That's an alternating current, right?
Yes, your radio signal is an alternating current. In fact, it alternates very fast.
Yep.
If you're on 20 meters, for instance, if you're on 20 meters, for instance, that's 14 megahertz. Megahertz is million cycles per second. So it's alternating from positive to negative 14 million times per second, which is very fast. Our power that comes out of the wall does so at 60 cycles per second, which is a very, very slow rate. First, we're going to look at capacitive reactance. And we all understand resistors. So if we have a 250 ohm resistor and we put it in series with another 250 ohm resistor, we know the total would be 500 ohms, and that in the middle between the two resistors would be a voltage divider. So if we took a capacitor, and now that would be for DC, if we had DC or AC. Resistors don't care whether it's DC or AC, they do the same thing. But if you get a capacitor, that blocks DC. But if you apply AC to this circuit, which here, I'll show you here. Is my mouse showing up on your end?
Yes.
Good, okay. So here's a 270 ohm resistor, and here's a 10 microfarad capacitor. Now, if we have a relatively low frequency, the voltage across this capacitor will be relatively high. If we have a high frequency, the voltage across this capacitor will be quite low. And I'm going to demonstrate that to you here in just a moment. So now here's a current probe. Now I was going to show you phase shift, and I've tried for 3 days with my current probe to make it work. I've done this before in this class 12 years ago, and it worked just fine. And now I can't get it to work at all. So I'm not actually going to be able to show you how the phase shift of a capacitor and an inductor work. I'm going to have to just tell you about it.
Well, Joe, maybe that old technology changed.
Well, I know one thing, physics hasn't changed. Capacitors, the current leads the voltage, and in inductors, the current lags the voltage. So that was a given, but yeah, it might have something to do with the equipment, because before I had a passive current probe, which plugged directly into the scope. Now I've got one with an active thing, and I think it's changing the phase angle. And anyway, it's not working. So hopefully I can work something else out. But let's take a look at this circuit right here, and we'll go over to my equipment that's set up over here. Okay, Daron.
Looks nice.
I'm turning the music back on.
All right.
Now, can you hear that?
Yes.
I need to get a little more prominent. Now watch what happens when we decrease the frequency. Notice the size of the signal. Now remember, there was a resistor and then the capacitor. So now as I increase the frequency, watch what happens.
Look at the amplitude now.
Oh, that's terrible. So watch it again. As we lower the frequency, the voltage goes up. So the reactance or the resistance of the capacitor goes down when the frequency goes up. So let's watch again. Here's very low frequency, and then we go up. And I'm going to mute that for a minute. Let's switch this around and let's go to an inductor. Okay, turning the noise back on. Here's a high frequency, and then we lower the frequency. So at a low frequency, the amplitude is low, and I don't know how I'm picking up this. I'm picking up some extraneous noise. But as we go up in frequency, the resistance increases, and the voltage across it increases. Does anybody have any questions about that? So, can somebody repeat back to me what I just said?
No.
No. Let me start out. I'll ask a real simple question. In fact, here, let me, excuse me, get back to this.
But that was an awesome demonstration of it. That was really good. I appreciate that.
Thank you, Daron.
You want to get off the musician's sound if you're not going to make more noise.
Oh, okay, inductive reactance. Here is the formula. Now notice this one, we're not dividing, but we're just multiplying. 2 pi times FL. And, you know, if you don't have a calculator, you can always go online and just enter inductive reactance calculator, and it will bring up several sites. And all you have to do is plug in the frequency and the inductance, and it'll tell you what the inductive reactance is. In fact, the site that I went to, you just click on one button and you could select any one of these. And then if you've got the other two, it'll tell you what the one is that you selected. So it's real easy to come up with the answers for this. But here we go. X sub L is the reactance of an inductor is 2 pi times the frequency and the inductance. So if the frequency goes up, the reactance goes up. If the inductance goes up, the reactance goes up. And we observe that when the frequency went up, the reactance went up. So, and here, F, of course, is in frequency in megahertz, and L is inductance in microhenries. But these sites that I've gone to, it'll ask you if you're, you can, or excuse me, I'll just put it this way. You can select whether your frequency is in hertz or kilohertz or megahertz. And so they're really, really handy. Okay, now for a capacitor.
Five minutes, Joe.
Thank you. For capacitors, here's the drawing. Here's the formula. 1 over 2 pi FC. So this is the inverse. The higher the frequency, the easier it is for it to go through a capacitor. So the reactance of the capacitor goes down with frequency, down. And the same thing here. You go online, you can find these machines, so you don't have to have a fancy calculator to figure it out. But any of you who are working on your general license, you need to know these two formulas, and very often one of these formulas will be required to know on the test. So
Joe,
go ahead.
so I have a question. When we're looking at the capacitive reactance or the inductive reactance, those formulas, the frequency is either in the denominator or the numerator, and that tells us whether increasing frequency is going to increase or decrease the reactance.
Exactly.
But that's measured in ohms, right? Reactance is measured in ohms. When you were illustrating that, weren't you showing volts instead of ohms?
Well, I was showing volts across the capacitor.
Ah, okay.
Oh, I'm sorry. I did not. Well, yeah, Yeah, I mean, here's the diagram here. This
Uh-huh.
was from my previous class, but this, here is the oscilloscope, here's the voltage probe, and here's the capacitor. So we're
Uh-huh.
measuring the voltage across the capacitor.
Okay. Okay.
That's a really good point. Thank you. Any other questions? Nope.
And likewise, when you had the inductor there,
Yeah, here.
yep, it's the voltage across the inductor.
Yeah.
Correct. Correct. By the way, the inductor that we used that I showed you was 10 Henry, not 0.85 Henry. It was 10 Henry. This was set up for the. I was going to show you the phase angle using the current probe, and you know, I'm honestly, I'm not sure how I'm going to explain this to you, but let me try. Oh, Daron, we're almost at 7:30, right?
Yep, you got 2 minutes.
Well, let's take a break. If you put an inductor and a capacitor either in series or parallel, when their resonance, when their reactance is the same for the frequency that you're on, that's called resonance. So if you're tuning something, you want to have both the capacitor and the inductor to have the same reactance. And when that happens, it is tuned. So that's how you get resonance. I have here the stuff that we've got coming up. Now, for those of you who are studying, now's the time to get out the book and look at chapter 4, the first section where it says mathematics. I want you to read it whether you understand it or not. But we're going to be getting into impedance and resonance. And we need to understand how to visualize that in rectangular or polar coordinates. And I will be prepared next week to explain that in great detail. But I've held you off from studying that till this point when you can start getting an appreciation for why that's useful. Because we're going to be talking about impedance. Now, does somebody want to tell me where impedance is used?
It's used on the output of my transmitter.
Right. And what is, you got a solid state transceiver, right?
Yes.
Yeah. So what is its characteristic output impedance?
50 ohms.
50 ohms. Okay, now your antenna, which is a hex beam, which works quite well for you, what is its impedance?
Its impedance is 50 ohms.
At what frequency?
Oh.
You
At whatever frequency I have it tuned to.
right. What
So
is it good on, like 20, 15, and 10?
Oh, on the hex beam, excuse me. I understand what you're looking for. That hex beam is good for 20 meters through 10 meters on my hex beam, and they make them, you know, the normal hex beam of that size, they make them for 20 meters through 6 meters also.
Oh, yeah.
So is there no balun on that, Scott?
No, I don't use a balun at all. I don't need a balun at all.
Okay.
That's a tuned circuit.
So, or a transformer, sorry, but yeah, transformer would be a better
Yeah, no
description.
transformer, and to keep the RF off of the out of my shack and so on, I have the oh gosh, what do you call the rings up there?
Toroids?
The toroids. Yeah, I have about 7 toroids over the coax.
And what do you call that, Scott?
Oh gosh.
It's an RF choke.
RF
Yep.
choke. That's right. It's a choke. RF.
And what it does is it keeps the signal from reflecting from the antenna and coming back down the outside of your coax.
Correct.
which can be important, especially if you're like some people we know who have been getting RF burns off of their radio.
Exactly.
And that's one of the things that happens. If you are at residence, and usually it's not a serious problem, but it can be.
Yeah. Well, I've talked to. I remember at one time, very early, in setting up my system, when I was talking with some folks that really knew what they were doing, they said, I can tell you've got RF on your in your shack.
Oh.
You know, and on some of those wonderful rigs like the IC 7300 and so on, you know, they've got a built-in scope basically.
Right. Well, that rig that you have at your house is really sounds nice.
Oh, thank you very much.
Yeah, that's really good.
Tintec was really noted for superior audio. Tintecs and the Kenwoods and so on.
Now, I want to ask you, is your on 20 meters, and that's where it's going to be the toughest. Does it cover all the way from CW through phone?
Yes, it does.
Oh, it does. Oh, okay, very good.
100 watts is.
Well, that means that the impedance stays better than a 2-to-1 ratio. In other words, it's within 50 ohms. It can be within from 25 ohms up to 100 ohms, and that's a 2-to-1 SWR. And that's the impedance that it stays within. So that's really good. Do you have a 80-meter dipole?
No, I don't. I had an 80-meter G5RV that I used as my antenna. It was really a nice antenna for and very economical. You know, I mean, you could get a real nice one that was set up for use out on the coast here, so you didn't have to take it down and redo the connections every 6 months to a year.
Yes.
Those would run you about $100, and as opposed to a hex beam, which is now like probably a little over $1,000.
Ouch.
You know. So at any rate, I had that up, and the thing I like about a hex beam is it only has it has a 9-foot radius, so I have to have a clear area of 10 foot to keep it from running into the limbs and so on.
Good.
And the area that I had for that, and which keeps it a lot less obvious to neighbors, by the way, too, as you know. That's right where my hex or G5RV used to run in that particular area too.
Scott, I want to ask you some questions about your G5RV.
Yeah.
Now, I won't dare ask Daron because he has this thing about G5RVs.
Yuck.
Well, the thing is, though, see, most people say yuck, but I find out that they're using them in an inverted V, and mine is strung like a regular dipole.
Either way, it's non-resonant on almost every band.
That's what
It is.
and you have to have a tuner. You gotta,
Yeah.
with the G5RV, you need to have a tuner. And I only use just the tuner on my Pentec. I didn't have a separate tuner, Daron.
Yeah.
Gentlemen, I would like to say something about that.
Yeah.
Something that I have always taught. If you have any antenna up at all, it will work. It may not work well, but it will work.
Yeah.
And if you can adjust the impedance to match it, it'll work with your transceiver.
Yeah.
But the G5RV is not resonant at any specific frequency. It comes close. It's about its best SWR. I think it was, I can't remember for sure, but I think it was 40 meters and is about 3.021, which would have meant that it would have been a third of 50 ohms or 150 ohms, somewhere in there of an impedance. So that meant that the impedance of the antenna did not match.
Uh-huh.
And what you're talking about is you have to use a quote antenna tuner to match the impedance.
Yeah.
Now I don't like calling them antenna tuners because what they are, they're transmatch, which I think
I agree.
the word
Yep.
that you used, Scott.
In reality, they're what? I don't have my hearing aid in.
They're a transmatch.
Oh yeah. Uh-huh.
Now, in order to figure out if you've got a transmitter that has a characteristic of 50 ohms impedance, it wants to look at 50 ohms impedance. It'll tolerate up to what they call a 2-to-1 SWR, which for a 50 ohm transmitter would be from 25 ohms to 100 ohms. When you have a mismatch, the voltages change on the antenna as they go up to the antenna. And if it doesn't match, it'll hit the antenna and the voltage will reflect and come back down the coax.
Yep.
When it does, it adds and subtracts from the signal that's going up the coax.
Yep. Yep.
So you end up with what's called a mismatch. In order to get a match, you need either to change something at the antenna or change something in your radio station using, and they call them a transmatch. Now, that's called impedance. And when you start working with impedance, you end up working with what are called, oh shoot, my mind just went blank, not magical numbers.
Imaginary numbers?
Imaginary numbers, yes, thank you. So it's like you're taking the square root of a -1, which is an impossible thing to do because you can't multiply anything by anything or square anything and have it come up being a minus number. So
That's right.
they use imaginary numbers. Well, they work, and you can represent what the impedance is by using either a rectangular coordinates or polar coordinates. And that will show you what it is. But in that, you have imaginary numbers. With that, and much later in the course, we're going to learn how to use oh shoot, now my mind went blank again, a Smith chart. And when you plot what your antenna analyzer says, if you've got one of these MFJ, what is it, 259? Would that be right? Antenna
Oh.
analyzer?
Some kind of number like that.
Yeah, something like that. It'll tell you that it's 125 ohms J 13 or minus J 42. By plotting it, you on a Smith chart, you can see what it actually is. You can tell what the real resistance is and what the imaginary resistance is, and you can also take those same numbers, put them on a Smith chart, look at the Smith charts, take a compass, rotate it around, and come up with what the in either the inductance or the capacitance that you need to bring the antenna back to 50 ohms. So that's something that we extras need to know how to do.
Yep.
Now, are there any questions on that? Because we're going to study this in much greater detail later. No questions? Okay, look, coming up, we're going to next week we'll be talking about impedance. We're going to do rectangular and polar coordinates. I don't know how far we will get. Be real nice if I can get through this whole thing. Daron, do you know anything about reactive power and power factor?
No.
You know, I just know they apply to motors. You know, if you got a 1 horsepower motor,
Sure.
it has a power factor of 70 or something like that, and you can work with that. You use capacitors to shift it. And I'm going to try to learn more so I can teach you guys what I don't know. So anyway, and then following that, we'll be talking about resonance when an inductor and reactor have the same capacitive or the same reactance. They are in resonance, and what happens in series resonance and in parallel resonance. And then we will be, and this is more for the extra class Q. I don't know if any of you know what Q is, and he's not a character in a Star Wars or Star Trek program.
Or James Bond.
That sounds more like it.
Anyway, Q is how good a tuned circuit is. If it's got a high Q, it's a very sharp resonance. If it's a low Q, it's a very broad resonance. Sometimes you want one or the other. And then this chapter 4 actually goes into magnetic cores, which for modern electronics is a pretty important topic. And so we will be going into that. So folks, does anybody have any questions about any of this?
Oh, Joe, I have so many. No, it's very, very deep material and very tough to deliver and for me to grasp at times. I appreciate your patience with it. I'm just not good at math and never have been. So I grasp it for a moment, while we're here talking about it, and then I'll forget it by morning. So,
Well, Darren, you are an extremely good technician. I mean, you do your work very well, but you have in your head a basic understanding of what happens and why. You might not be able to do like engineers do. And honestly, when I was working on this stuff tonight, I had to go online and actually I'm going to take you to that. Hopefully I will find it here and use the online formulas. Now you guys can see this.
yep.
So I was trying to figure out something that I could use for for showing excuse me, phase shift. And I have a whole bunch of inductors, but the first one I grabbed was not working. I was using Darren's technique. Grab one, hook it up, and see what happens. And I finally decided, well, I need to figure out what's going on. So I needed to know what size of an inductor I need. So I went to this and I clicked on inductor, and then I put in 60 hertz because I was going to use a 24-volt transformer. And so I want to know what the inductor is. So I hit calculate, and that didn't work. What did I do wrong?
You're missing a value somewhere, I think.
Yeah, maybe I'm. Oh, that's what I want. Inductive reactance, inductance. No. Oh, here, I figured about 270 ohms. So that's a 0.7 Henry. And at 270 ohms, and hopefully, I'm not going to show you what I went through, but this is what I came up with. Now here is the calculations that I started working on in order to figure out how to produce enough current so that my current probe would work. Because the first examples that I used where I showed the reactance, it did not put out enough current for the current probe to work. So I had to get something down so it'd show a few milliamp. So the first thing I did is I looked at 60 hertz. My pointer here, 60 hertz at 10 microfarad. And that reactance was 265 ohms, and I used that online meter to figure that out. So I thought if I used a 270 ohm resistor, that would divide it in half. So I doubled that. So I ended up with, I want to know what the current was going to be. So that's E over R. So it's 24 volts AC, which I had a 24 volt AC transformer, and I had 535 ohms. By adding this resistance, and this is a standard resistor size. So I added them together and I'd come up with 0.045 amps, which is 45 milliamps, which my current probe should have worked, but it didn't. Then the other thing I had to figure out is how big a resistor I needed. So I used this formula here, power is equal to I squared times R. So I took 0.045, squared it, and multiplied it times, well, I use 270 ohms at 12 volts AC. So that came out being 0.5 watts. So I needed at least a half watt resistor. I would have looked really silly if I'd used a quarter watt resistor and it smoked while I was in the process of demoing. So then I tried to figure out the inductor. So I had a 10 Henry inductor. So I used the calculator to come up, and it came up with almost 3,800 ohms, which was way too much because the current of 3,800 ohms would be just a tiny fraction of this 45 milliamps. And that would have never showed up on my current probe. So I had one capacitor that was, or one inductor that was 1.7 Henry. And oh, by the way, I have this device. And if I power it on, so it's ready to measure, but I'm going to turn it on inductance. And it says it's not an inductor. So I'll put these on here. And then I will hook them together. It says it's 0.24 microhenry. But there's a 0 button here, so I can press this. And it zeroes that out. And then, hopefully, here's a transformer. Transformer is 2 inductors hooked up in parallel. So if you disconnect the output, then it'll be its maximum inductance. So the, I'm having trouble with the,
Right in the beam of the light there.
yeah, I know, I'm trying to.
There you go.
Oh, pretty cool.
1.15 Henry, which is this transformer is too big for what I wanted to do. So I tested. I tell you, I had a box full of these old transformers. Oops, excuse me. These guys here. I mean, these are the old wall warts that didn't use switching technology. And so, but they're a good source of inductors. Anyway, this device, I bought it many years ago, and I actually built this one. And it cost about $100. And I've got $1,000 worth of use out of it. But you can buy these things now for $30 from China, and it does everything this thing does. So this is a real handy device. But anyway, using this device, I was able to measure several of the inductors that I had. And I came up with, if I used 0.7 Henry, that's about 270 ohms. And it turns out I had a one that was 0.66 Henry. And that's what I used to try to show you how phase shift worked. Problem is I had no phase shift, and the AC signal looked like it had been run over by a Mack truck. It was really an ugly thing. So anyway, these are the kind of things that I went through to figure out how to do this. And of course, you know, our friend who's an engineer, who's quote in the class, who was teaching me how to do some of this mathematics. He would do this at a drop of a hat. But anyway, I also figured out what the power was being dissipated in the inductor, and it came out the same thing, 1/2 watt. So that's what I went through for this class tonight. And that,
Joe,
yes,
it sounds like if it looked like it had been run over by a Mack truck, that maybe you had something that was a very low Q.
well, instead of a sine wave, it looked like a mutilated sine wave. It looked more like a. Has anybody ever seen an inverter that's it's not a true sine wave? They kind of call it a modified
yeah.
sine wave.
Oh, yeah, those are horrible.
Oh yes, yeah, they're well, they used to be just about all that was available. I've sold lots of them. But anyway, it looked closer to that. And the current was in phase, and even worse, it was even worse mess. So I don't know. Anyway.
Well, Joe, I was going to offer, I know next week I'll be in Scotland. The week after that, I'll be in Klamath Falls working. But the resonant circuit thing, I was going to offer to do that in a little transmitter.
Oh,
Where you can, well, maybe if it'll focus, where you can see a series of inductors and capacitors on the output.
Oh,
And, each one of those is tuned to maximize the RF out so they become resonant at whatever frequency we're using. And it's really easy to see with a watt meter or a voltmeter as you go through and adjust those capacitors and squeeze or spread those coils to get each stage resonant.
cool.
So that's where that part really, resonates for me. And I got to answer the phone.
Okay, thank you, Scott. Well, and if nobody has anything else, I think I'm going to call it a night.
yeah, I was going to show you it's a diagram showing a high Q and a low Q
Oh,
Oh,
with the narrow bandwidth for the high Q and a wide bandwidth for the low Q circuit.
just hold it by your face, right in front of your face. Oh,
yeah,
no. Yeah, I don't
that's
know. Scott, do you have on your Zoom, do you have it set to blur your background?
Yeah, just a second.
Yeah, undo that. I had to learn that.
So that's another easy thing from the practical side for me to show with a couple of bandpass cavities, Joe.
Yes.
Where we look at them with VHF in VHF or UHF range, and I can change the coupling, how much we couple to that actual cavity. And you can see, looking at the skirt on the scope, how much coupling is taking place. Yeah, that's a perfect shot, Scott.
Okay.
Yeah. Yeah. Okay. Here, I don't know if you guys can see my mouse.
You're not sharing, so no. You'd have to share that screen for us to see it.
Yeah.
What book is that, Scott?
Oh, pardon?
What book is that?
That's what I'm using for all my, or a lot of my formulas and some of this work here. This is Electronics, second edition, a self-teaching guide by Harry Kybet.
Oh, interesting.
And just to give folks comfort, and show them that these equations really don't change. This is from 1986.
Yep.
I have some ARRL handbooks from the 1950s. It's all the same.
Yep, yep. And I've got, I've got an antenna handbook that is this thick. Now, the latest ones that are out, and about the size, about like this. Amazing how big it is. The one back in the 50s that has the same equations in it is that thick and about that size.
Yeah, I've
I
got
still
some of
got
those
it.
old
I
ones
still use
too.
it.
Yeah, you bet.
Well,
It's handy.
Darren, you don't need to apologize for not knowing the mathematics, because you sit down and you do the very things that the engineers have to try to figure out with mathematics. You just sit down and do it and it works.
Well, I'm very practical, Joe, and I just never got that formal AC DC theory training early on, and I really would have helped me a lot if I'd have gotten that. But everything has been kind of on the fly with what I needed to know, so it's a very practical orientation. But
Oh yeah,
I respect the theory. I just don't really always get it. I'm more of a practical person.
yeah. Well, you know it really well. I was fortunate because when I went to Tektronix, they had classes and they had some fantastic instructors, and they taught us a lot of stuff. I wish I could remember it all, but I can't. Anyway, okay. Anybody have anything else?
Well, just a big thank you to you both. Uh,
Yeah, thanks, Joe.
Oh, thanks, you guys. This is one night I really need it. I was really tired and I was getting frustrated, and I came in here and the internet didn't work. The cable had been cut. Oh, gee. And I was trying to get stuff set up for you, and I was trying to do the current probe and the phase shift for capacitors and inductors, and it did not work. And that was really frustrating. So, hey, Darren, on your picture there, I see the coils and the capacitors across the bottom. And
Yes.
on the left-hand side, there's something there with, I can't tell quite what it is.
Well, which left-hand side is that over here?
Yeah, that right under your feet, that thing. What is that?
That is the output, and it's an RCA type connector on the output of this board
Oh,
with
now I
with a
see.
piece of a shielded RCA fitting soldered onto the coax there.
Now I see what it is. That looks
It's a little
really fancy.
it's a little 4-watt UHF synthesized transmitter.
Wow. What 70 centimeter?
Yes,
Yeah, okay. All right.
made by the great company Hamtronics, who is no longer in business, but they made a lot of fun stuff.
Yeah, there's a lot of those companies gone by the wayside. Heathkit was my absolute favorite one that really bit the dust.
Yeah, that was sad.
yeah, it sure is. I've still got an old Heathkit DX40 in my ham shack.
Oh yeah.
Nice.
Yeah.
You got a big hand truck to move that thing around?
Oh, heck yeah. I got
Oh,
that,
dear.
and that's and then sitting on top of that is my Hammerland HQ110 that I used to dream about. I had an NC88 for my receiver way back then. But those are all, gosh, they're like this size.
Yeah.
Yeah. Well, they don't call them boat anchors for
That's it. That's it.
for no reason at all.
Right.
Oh, and alongside that, by the way, you'll get a kick out of this. That was a crystal operated unit, that DX40, and right alongside of it, I've got my night kit VFO.
Oh, oh wow.
Yeah.
Yeah, I was a novice in the 75 watt, and you had to be crystal operated.
Uh-huh.
And I think I had 2 crystals.
Yeah, yeah, that's it. You
Yeah.
know?
I operated mostly on 15 meters, 21 megahertz.
Yeah. Well, I was operating back in the late 50s, and 58 through 1960. I went in the Air Force in 1960, late 1960. But at any rate, that's when the bands were really, really good
Yeah.
back in that cycle.
All right, Joe, you're making me tired.
Oh, yeah. The 15 meters would just follow the sun. In the morning, I was on the West Coast, and in the morning, the East Coast would come in, and midday, South America would come in. And in the afternoon, the islands.
Uh-huh.
Wow. Nice.
So, yeah, oh shoot, Don or Dan, Don, I think the Tektronix guy,
Oh, Don Tucker.
Don Tucker, yeah, he found my novice call sign, and actually, let's see here. I know in here somewhere. That's me. It was. It's not. Oh, here it is. No, that's not it. I don't have it written down. I started to write it down. I didn't write it down.
You don't know it by heart?
No, no. For years I was going. I can't remember what it was, and he found it for me. And I have novice license, and then it's blank. Shoot, I've got to go back and find his email and do that.
Ah.
Anyway, everybody,
Well,
I want to say good night.
all right, Joe.
And
So
thank-
I,
thanks-
what's it
thank you,
look like
Mr.
for Monday for fixing that cable?
I think that's a possibility, but let's talk about it later.
Should we talk about it over lunch Monday?
Yeah, well, hang on.
If
Oh,
we
you're
do lunch, I'm not gonna want
You,
to.
you really got his attention there, Daron.
Yeah, I know. He had to get his calendar out. Stop recording, Joe.
oh. Okay.